Hello everyone, we are going to learn about cyclic group and some examples. Cyclic group. A group G is called cyclic if for some A belongs to G, every element X belongs to G is of the form A to the power n, where n is some integer. The element A is then called a generator of the group G. There may be more than one generators of a cyclic group. If G is a cyclic group generated by A, then we shall write G is generated by A, that is G is equal to A inside the parenthesis. The elements of G will be of the form dot 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 a raised to the power minus 4, a raised to the power minus 3, a to the power minus 2, a to the power minus 1, a to the power 0 is equal to E, where E is the identity element of the group G, a square, a cube, a to the power 4 dot dot dot. They are not necessarily all distinct. Example 1. The multiplicative group G is equal to 1 minus 1 I minus I is cyclic, as we can express its members as I square, I cube, I to the power 4. That is I square is equal to minus 1, I cube is equal to minus I to the power 4 is equal to 1. Thus, G is a cyclic group and I and minus I are generators of the group G. Example 2. The group Zn is equal to 0, 1, 2 up to n minus 1 addition modulo n, where n is greater than or equal to 1, is a cyclic group. 1 and minus 1 is equal to n minus 1 will be its generators. But it can have more generators beside these. Let us consider Z8 is equal to 0, 1, 2, 3, 4, 5, 6, 7 addition modulo 8. Then we can check that 1, 3, 5, 7 will be generators of Z8, because Z8 can be generated with the help of 1, 3, 5, 7 respectively. We can see that 3 to the power 1 is equal to 3, 3 square is equal to 3 plus 3 is equal to 6, 3 cube is equal to 3 plus 3 plus 3 plus 3 is equal to 9, which is equal to 1. If 9 is divided by 8, then remainder is 1. 3 to the power 4 is equal to 3 plus 3 plus 3 plus 3 is equal to 12, which is equal to 4, because if we divide 12 by 8, then remainder will be 4, and so on. That is, group generated by 3 is equal to 3, 6, 1, 4, 7, 2, 5, 0, that is equal to Z8. So 3 is a generator of Z8. We also observe that 1, 7 and 3, 5 are each other's inverses, because 1 plus 7 is equal to 8 is equal to 0 and 3 plus 5 is equal to 8 is equal to 0. Also 4 is inverse of 4, that is 4 is self inverse. Example 3. The additive group of all integers z plus is cyclic. The generators of z are 1 and minus 1. Some properties of cyclic groups. Theorem 1. Every cyclic group is an abelian group. Let G is equal to A inside the parenthesis be a cyclic group generated by A. Let X, Y be any two elements of G. Then there exist integers R and S such that X is equal to A to the power R, Y is equal to A to the power S. Now X into Y is equal to A to the power R into A to the power S is equal to A to the power R plus S is equal to A to the power S plus R, because R and S are integers, so R plus S is equal to S plus R by commutativity of Z is equal to A to the power S into A to the power R, this is equal to Y into X. Thus we have X into Y is equal to Y into X for all X, Y belongs to G. Therefore, G is abelian. Theorem 2. If A is a generator of a cyclic group G, then A to the power minus 1, that is A inverse, is also a generator of G. Proof. Let G is equal to let G be a cyclic group generated by A. Let A to the power R be any element of G where R is some integer. We can write A to the power R is equal to A raised to the power minus 1 whole raised to the power minus R. Since minus R is also some integer, therefore each element of G is generated by A to the power minus 1. Thus A to the power minus 1 is also a generator of G. That is, A inverse is also a generator of G. Theorem 3. Every group of prime order is cyclic. Proof. Suppose G is a finite group of order P, where P is a prime number. We have to show that G is a cyclic group. We know that an integer P is said to be a prime number if P is non-zero, P is not equal to plus minus 1, and if the only divisors of P are plus minus 1 and plus minus P. Since G is a group of prime order, therefore G must contain at least two elements. 2 is the least positive prime integer. Therefore, there must exist an element A belongs to G such that A is not the identity element E. Since A is not the identity element, therefore order of A is definitely greater than or equal to 2. Let order of A is equal to m. If H is the cyclic subgroup of G generated by A, then order of H is equal to order of A is equal to m. By Lagrange's theorem, m must be a divisor of P, but P is prime and m is greater than or equal to 2. Hence, m must be equal to P. So, H is equal to G. Since H is cyclic, therefore G is cyclic and A is a generator of G. Theorem 4. Every subgroup of a cyclic group is cyclic. Suppose G is equal to A is a cyclic group generated by A. Suppose H is a subgroup of G. If H is equal to G or if H is equal to G or E, then H is cyclic. So, let H be a proper subgroup of G. The elements of H are integral powers of A. If a to the power s belongs to H, then the inverse of a to the power s, that is a to the power minus s, belongs to H. Therefore, H contains elements which are positive as well as negative integral powers of A. Let m be the least positive integer such that a to the power m belongs to H. Then we shall prove that H is equal to group generated by a to the power m, that is H is a cyclic and is generated by a to the power m. Let a to the power t be any arbitrary element of H. By division algorithm, there exist integers q and r such that t is equal to mq plus r, where 0 is less than or equal to r less than m. Now, a to the power m belongs to H implies that a to the power m raised to the power q belongs to H by closure property of H. By closure property in H implies that a to the power mq belongs to H, implies that a to the power mq raised to the power minus 1, that is inverse of a to the power mq belongs to H, implies that a raised to the power minus of mq belongs to H. Also, a to the power t belongs to H, a to the power minus mq belongs to H, implies that a to the power t into a to the power minus of mq is equal to a to the power t minus mq belongs to H, implies that a to the power r belongs to H, as t is equal to mq plus r, so t minus mq is equal to r. T is equal to mq plus r, so t minus mq is equal to r. Now, m is the least positive integer such that a to the power m belongs to H and 0 less than or equal to r less than m. Therefore, t must be equal to 0. Hence, T is equal to mq. So a to the power T is equal to a to the power mq is equal to a raised to the power m whole raised to the power q. Thus, every element a to the power T belongs to H is of the form a to the power m raised to the power q. Therefore, H is cyclic and a to the power m is a generator of H.